Welcome back to our study on statistical mechanics. We have been studying about classical statistical mechanics, and in our earlier class I had just introduced to you the conditions for a system to be classical or the system to be a quantum system. Now, in this section, what I am going to teach you is how the system can be made a quantum system. What we have is only classical statistics. The basic principles of statistical mechanics gives you only the ideas about a classical statistical mechanics. Based upon that classical statistical mechanic principles, we have to develop the quantum statistical mechanics. You can independently develop quantum statistical mechanics, but that is not to be done in this section. What we are doing is, we have our old traditional classical statistical mechanics rules and regulations, and we will be modifying those things suitable for a quantum system. Therefore, whenever I say a quantum system, that system will be exhibiting a large number of quantum phenomena. Classical phenomenon, we know about classical phenomenon. For example, Earth is revolving around the Sun, Moon is revolving around the Earth. There is no quantum problem connected with that. Macroscopic systems. If a simple pendulum oscillates, we do not require any quantum mechanics or quantum statistical mechanics to show that T is equal to 2 pi into root of L by G. Similarly, if you want to find out any equation for Young's modulus, or if you want some acceleration, velocity or displacement of a particle, we will not apply quantum mechanics or quantum statistical mechanics. Those phenomena we call it as classical phenomena. Now, there are a large number of other phenomena. For example, the best example is black body radiations. You have the Earth revolving around the Sun. I told you it is classical statistical mechanics. But at the same time, the Sun is radiating. The Sun is giving out radiations. What are these radiations? And why these radiations are coming out of the Sun? What is the basic constituent of these radiations? You cannot explain all this phenomenon, all these things by the help of classical statistical mechanics. You will have to develop a different branch of statistical mechanics, which we collectively call it as quantum statistical mechanics. Therefore, basically, what are black body radiations? We will be dealing with the black body radiations. It was actually in 1900 Max Planck put forward the basic ideas of black body. He derived the expression for black body radiations, considering that the energy of a particle is E is equal to h nu. Therefore, we want to, large number of other phenomena are also there. If you want to find out what is the specific heat of a solid, we have to take into account the phonons inside the solid, which is basically a quantum particle. Similarly, the very important prediction based upon the ideas of Satyendranath Bose, an Indian physicist, Albert Einstein put forward Bose-Einstein condensation, which is purely a quantum phenomenon, Such things, if you want to explain or if you want to study about them in detail, we have to consider quantum statistical mechanics, or we have to develop quantum statistical mechanics. And that how to develop that quantum statistical mechanics, we will be dealing here. Therefore, any quantum phenomenon, in the case of a quantum phenomenon, we will be using, or we will be, the particles that are taking in part will not be, for example, in the case of in the earlier example, I took Earth revolving around the Sun. Earth is not a quantum particle. And all these phenomena that I told you earlier, which are called as quantum properties, they will be exhibited only by these fundamental particles, basic constituents like electrons, protons, neutrons, photons, etc., which they will be having an integral spin. They will be having a spin, and that spin is basically a quantum property. That intrinsic spin will be a quantum property. We will have to take into account these quantum properties if we want to derive an expression for, or we want to convert our classical statistical mechanics into quantum statistical mechanics. And this thing I had explained to you. And in order to account for this quantum phenomenon, we will have to take the properties of these particles. The particles that I told you earlier, electrons, protons, photons, etc. And what are the special properties that are possessed by these particles which are living in the micro world? All these particles are living inside a system, or they are inside a system, and these particles, they exhibit a very interesting property, and those properties are, they are all identical. When I say identical, if I have two electrons, which now presently I label them as A and B, and if they are separated by a distance, if I change A is at one position and B is at another position, if I interchange their positions and find the property once again, then there will be no change in that property. Then I say that the first electron A is identical to the second electron B, and such property is known as an identical property of all the elementary particles, all the fundamental particles, all these microparticles, they will be having identical nature. The second is, all these particles, they must have this dual nature. That is, they will be having wave nature also, particle nature and wave nature also. That wavelength, all the particles in the micro world, depending upon the temperature, and that property of the wavelength will be called as de Broglie thermal wavelength, which we studied earlier. As the temperature changes, their wavelength also will be changing. When the temperature is increased, the temperature is decreased, their wavelength will be increasing. And this wavelength will be responsible. The bigger the wavelength, the more aggressive the quantum property will be. And finally, the last point is, they will be possessing spin also. They possess spin also. I told you that all these particles are classified into two depending upon the spin. The particles having 0, 1, 2, 3 spin are called as bosons. Particles having odd half integer values, odd half integer, that is 1/2, 3/2, etc. They are called, we call them as fermions. We call them as fermions. And these properties are responsible for the quantum property. A system which is a quantum system, they will be exhibiting the quantum properties like black body radiations, the specific heat of a solid, then Bose-Einstein condensation, etc. All these are due to these three properties I just mentioned. And these properties has to be taken into account if I want to explain what is a quantum statistical phenomenon. All these has to be taken into account, and they must be put together, because these particles possess all these properties simultaneously. Therefore, all these properties must be put together, and then by taking all these properties as a single entity, and we have to change our classical statistical mechanics to quantum statistical mechanics. And for that, one more property which I forgot to tell you, but a very interesting property, or a very important property, which is known as the indistinguishability property. Indistinguishability means the particles will be possessing, for example, they must be in such a way that the wavelength of the first particle or the wave nature of the first particle will be overlapping with the wave nature of the second particle. If you have two particles which are behaving as particles, then the first particle and the second particle will be perfectly distinguishable. But if these particles are in the form of a wave, for example, if I have a particle here and if I have a particle, I can very well distinguish them. But if this particle in the micro world, if this is in the form of a wave and the second one is in the form of a wave, then these wave functions overlap. And when these wave functions overlap, I cannot distinguish the first one from the second one. Such a property, only if the system possesses, or if the particles possess such a property, only then you can say that the system is now having a quantum behavior. Such a property is known as indistinguishability property, and the particles must show such a property also. Only then we can say that now we have a quantum phenomenon. Therefore, taking these four ideas into account, we are going to define a new parameter which is called as all these things I have told you earlier. New parameter which is known as the occupation number. All these four properties will be taken into account. all this, taking into account all these properties, I defined a new parameter which is called as the occupation number, which is represented by the letter Ni, and that Ni will be equal to 0 or 1 for a fermion. Ni will be equal to 0, 1, 2, 3, etc. up to infinity. Any value for Ni is possible. Such values we will be attributing to bosons and fermions, and then these values will be put back into our classical statistical mechanics. For example, in the case of fermions, Ni is 0 or 1. Ni is equal to 0, 1, 2, 3, etc. up to infinity. For example, if I label or if I take a system, what fermions says that, or for the case, because we have two types of systems, one is Fermi systems and the second one is Bose system, that is bosons. If I label a state like this, because of the nature of the spin, all the 4 properties that I told you, in this particular state only one particle will be allowed to occupy. Either the state will be empty or the state will be filled by a particle. If the state is empty, I will call it as 0. If the state is filled by a particle, I will label that as 1. And such a number, we call it as the occupation number. It is a particular representation of the quantum. If I want to represent the quantum property, I am going to represent my system like this by introducing this occupation number. I will call if the complete state is empty, I will label it as 0. If the state is fully filled, I will label it as 1. But in the case of a boson, if I have a state, the state can be empty, but otherwise it can be filled with one particle, it can be filled with the second particle, it can be filled with the third particle, it can be filled with the infinite number of particles. But remember, the state means, in the case of a quantum system, the state means it is a wave nature, it is a wave. Therefore, this state means it is this wave itself is the state. Therefore, when I say that there are two particles in the same state, actually what I am doing is I will be adding the second particle or the wave of the first particle with the second particle. If this is my second particle, these two will be added together and I will be getting a bigger wave. This is the two particles in a single state. Two particles in a single state. This is the first particle, this is the second particle. If I say that they are in the same state, I cannot represent like this. If I represent like this, these two are in different states. Even though it is a state is represented by like this, I cannot say that they are in the same state because there is a separation between them. When I say they are in the same state, this and this will be added together and I will get a new state, that is two particles in the same state. Therefore, this is the way of representing, or this is the way in which you will be able to introduce all the quantum properties into the system, all the quantum properties into the system. Therefore, I am going to take occupation number 0 and 1 for the fermions and 0 to infinity for the bosons, and then I will be changing my old classical statistical mechanics. And to change my old classical statistical mechanics, the best ensemble is grand canonical ensemble, where the partition function is given by sum over n, ni z raised to n qn, where qn is the canonical partition function. And earlier I had represented my capital N. If I want to introduce my occupation number, the capital N will be sum over ni, where ni is the occupation, sum of all the occupation numbers, and here this ni will be, this energy will be represented by, this was z raised to n e raised to minus beta e, and that e I will change it as sum over I ei ni. Remember, this ni will be now here not the number of particles in each state, it will be the occupation number of the particles, occupation number. Therefore, I will replace this set by this expression, and by using some mathematics I will rewrite all these things and I will be getting my expression for the partition function, for the grand partition function for the this Fermi-Dirac system will be, I am taking this this Ni I take as 0 and 1. If I take Ni as equal to 0 or 1, I will get my Fermi-Dirac statistics like this, the partition function for the Fermi-Dirac statistics like this, and my Bose-Einstein statistics will be represented by like this. Okay. What I had done is I have this grand partition function which is given by z raised to n qn, z raised to n qn. Then I will represent my n as equal to, now it is the sum of the occupation numbers, and this qn contains sum over e raised to minus beta e, and this e I will be representing as sum over I ei ni. This ni is now occupation number. I will put back this into this expression, and then I will get ni. When I simply substitute these values with ni equal to 0 or 1, I will be able to get a new partition function z, which I will call it as Fermi-Dirac partition function, which will be product of 1 plus z e raised to minus beta epsilon, e raised to minus beta epsilon. This will be Fermi-Dirac grand partition function, and if it is for Bose-Einstein, this will be product of 1 minus z e raised to minus beta epsilon. This is product of different energy states, product of different energy states. This is for Bose-Einstein one, and this is for Fermi-Dirac. Therefore, you have the partition function for Fermi-Dirac is equal to product 1 plus z e raised to minus beta epsilon. You have in your grand canonical ensemble, you have PV by KT is equal to log z. I will write here. U is equal to KT square dou by dou t of log z, and you have n is equal to Ez dou by dou z of log z. All these require log z. If you want to find n, I require log z. If I want to find u, the internal energy, I require log z. If I want to find pressure, I require log z. Therefore, I will convert this z, which is given as the product of energy states, into log z. Therefore, if I take a logarithm, this represents the product. Logarithm of a into b is log a, sum of the logarithms, log a plus log b, log a plus log b. Therefore, if I find logarithm of z, that is for Fermi-Dirac statistics, I will be able to get that as sum of the logarithms, sum log 1 plus z e raised to minus beta epsilon. This is for Fermi-Dirac statistics, and log z will be equal to, when I take logarithm, I have that minus 1 divided by product will be there, then I will be getting logarithm, that is minus sign, log 1 minus z e raised to minus beta epsilon, beta epsilon. That will be for Bose-Einstein statistics, and the other one will be for Fermi-Dirac statistics. Therefore, these are the two expressions, and from this log z, I will be able to get all the thermodynamics. I will give you some, I will give us two questions I will give you. Two particles are said to be distinguishable when? When will you say that the two particles are distinguishable? The two particles will be indistinguishable means the wave functions overlap. Therefore, if these wave functions are not overlapping, we will say that the particles are distinguishable. The average distance between them is much larger than the de Broglie thermal wavelength. The average distance between them is smaller than the de Broglie thermal wavelength. They have overlapping, that means it is a quantum system. That if the wave functions are symmetric. The correct answer is the first one, the average distance between them is larger than the de Broglie thermal wavelength. The particles are well separated. The second question is, it is necessary to apply quantum statistics to a system of particles. When will you apply quantum statistics for a system of particles? We can apply quantum statistics only when the wave functions overlap. That is, if there is a substantial overlap between the wave functions of the particles. Okay. Therefore, the answer is A. Therefore, we have studied about in the case of quantum systems, we have studied two sections. In the first section, what I had shown you is what are the conditions for the system to be a quantum one. Basically, we derived the condition for a classical system which is n lambda cube much less than 1. And the second case, what I had shown you is that how your classical statistical mechanics ideas or the basic equations can be converted into quantum statistical mechanics. To get our quantum properties, what we want is a new equation, new partition function. Therefore, incorporating the quantum properties, we had derived the new partition function for Bose systems and Fermi systems. And then these partition functions can be compared with the old basic thermodynamic equations. Therefore, now we are in a state to study about quantum systems like Bose systems and Fermi systems, which we will be studying as separate Bose-Einstein statistics and Fermi-Dirac statistics. I hope all these things you have understood well. Now, we will see Bose-Einstein statistics and Fermi-Dirac statistics in the next two sections. Thank you.